Okay, so Assalamualaikum, a very good morning, everyone. So thank you for joining this session. So this is ENT243, or nowadays the new code is MMJ22403, Thermodynamics 2. So please make sure that you guys are in the right session. All right, so for today, we are going to cover the introduction to Thermodynamics 2. And just to recap, the course coordinator for this course is Associate Professor IR TS Dr. Nasrul Amri Muhammad Amin, and myself, which is Anas Abdul Rahman. So we will be teaching this course for this semester. So before we proceed even further, please make sure that you guys have watched the video that I've posted for this week for the asynchronous session on Monday. Okay. So as you can see here, the timetable as given by the school or the faculty. So I think this is the latest time slot given to us. So we will have our asynchronous on Monday at night, and then we have 1, 2, 3, 4, 5 lab groups designated for specific group. Okay, we have X diploma, we have year 2 intake, and then on Friday today we have our synchronous lecture. So please make sure you are aware of this schedule. Okay, and just to again to highlight the importance of understanding what you are going to learn and achieve hopefully by the end of this semester. In total, we have 3 outcomes for this course, and this outcome basically is aligned with the chapters in your book. Okay, so for example, the first CO, CO1, is about the ability to create solutions for problems in gas, vapor, and combined power cycles. So this relate to chapter 9 in the textbook. Okay, and for CO2, its ability to create solutions for problems in refrigeration and air conditioning cycles. Okay, so sorry, for CO1 is a combination of chapter 9 and chapter 10. Okay, and CO2 is after that. And finally, CO3 is the ability to analyze the problem in chemical reactions, adiabatic flame temperature, and phase equilibrium. So for this semester, the course or the semester will be divided into 2. So I will take charge of the first CO, which is the ability to create solutions. So I will deal with gas, vapor, and also combined power cycles. And then Dr. Nasrul Amri will take over with refrigeration cycles as well as for the chemical reactions, CO3. Okay. The complexity level is as stated here. So I have already discussed or explained about the complexity level. If you can see over here, even the keywords used in the course outcome is basically self-explanatory. Yoli, could you please mute your microphone? Thank you. All right. Okay. So, for example, C6 or the cognitive level 6 basically is the highest cognitive level that basically will test student their ability or the understanding of the topics in regards to creating the solution. So we'll give you a problem, and students have to come up with a solution to that problem. Ma Yongli, could you please mute your microphone? Okay, thank you. All right. So, so this is just a heads up. So meaning that your test or your final examination will reflect to the complexity level. Okay. Similarly, for CO2, we will also test your understanding in terms of creating solutions for the topics or for the contents that were taught. Okay. CO3, however, we will basically test your understanding up until C4, which is just analysis. So you have to analyze, come up with a solution for that particular problem. Okay. So for possible assessment, I think it's quite standard. We will have assignment, quizzes, labs, and examinations. Okay. Um, do you have any questions about what we have covered so far during the asynchronous session as well as up until this course outcome? If you got any questions, please just unmute your mic, or you can ask in the chat box. So, okay, all right. So from the chat box, okay, Amalin. Okay, Amalin. Okay, thank you, Amalin, for letting me know. All right. So I understand that some of you are still at home, and basically according to the schedule, you have to plan your journey. So I understand that. That's okay. So thank you for Amalina for letting me know. All right, for the rest of the group, okay, before we go into details about this matter, I'm just going to proceed a bit about the registration, okay? So I believe most students already got this message in their respective group, WhatsApp group, from either Dr. Rizwan, our PR, or Mr. Azizul, which is the coordinator for RPS. So I think we have international students here, so I'm just going to translate this. Basically, for cohort, basically if you're in your second year, and you are taking this course for the first time, and your program code is UR something, UR6521001, then you can proceed by using the latest code, which is MMJ22403. Okay. However, for students who are repeating this course, okay, where your program code is as highlighted over here, you are still under RK08. This is the old code. So if your program or if your cohort is still under RK08, please register by using the old code, which is ENT243. Okay? And from the system, I checked this morning. Actually, we have quite a few numbers of students who are repeating, and they are registering the wrong code. Okay, so I think Dr. Rizwan already sent out this message to everyone. So please, if you are repeating this course, okay, so let me highlight this. So repeating students, if you are repeating this course, so kindly register by using the old code, which is ENT243. Okay, otherwise you will have trouble because your transcript cannot basically recognize the latest code because it is not planned under your curriculum structure. So it's very, very important for students to follow your own curriculum structure. Okay, this is very, very important. If your curriculum structure mention ENT243, then you have to register for the ENT243 code. Okay, but you can still join this session, by the way, because Thermodynamics 2, the content is similar to the previous ENT243 that was offered several semesters ago. So those students who registered for ENT243, you can still join this session, but you must register under the old code. Okay, I hope I made myself clear, and I believe Dr. Rizwan already blasted this WhatsApp, this image, this information in the WhatsApp group. Okay, so please take note. The repeating students, please register by using the old code. Up until this morning, when I checked the system, there are still a lot of students who are repeating, registered using MMJ code, which is wrong. And when I check the ENT registration, basically it's still empty, meaning that students basically make the wrong registration for those who are repeating. Okay. Any questions about this matter? Okay, I would appreciate any feedback if you got any questions. Okay. All right. So now, in regards to the message by Amalina. So basically, Amalina, one of your friends' message is she said that she can't join this class because she's on her way to UNIMAP. Okay. I understand that this is the basically transition or the phase where students who are still at home must come back to the campus. So that's okay, that's fine. Okay, I understand that, but please let me know, like what Amalin said. so that I can keep note and basically put some notes in the attendance sheet. All right, so regarding attendance, as you all understand that I have posted the first asynchronous video, which is regarding the briefing or what is the expectation, what is going to be covered in this course from Monday's session, asynchronous session. However, based on the latest data that I looked this morning, so from the system, we have 120 registration, okay, from official registration. So in the Google Classroom platform, we have 125 students who enroll for this class. So there are probably about 5 students here who are yet to register. Probably they are doing manual registration, so that's okay. But out of these 125 students, there are still 39 students who did not submit the attendance form for the first class, which is asynchronous. All right. So as I said, I understand that some of you are just joined this platform. Maybe you just realized you need to repeat, or maybe you just realized that you need to take this course. That's okay. So I will open the attendance for week 1 for both async and sync up until next Monday. Okay. All right. So this is a special chance that I gave because I understand during the first 1 or 2 weeks there will be a lot of confusion. It's very dynamic, students registering and then dropping out of this course. So that's okay. So I will give students, these 39 students, up until next Monday to complete their attendance form for week 1. Okay. Similarly, for students like Amalin, who basically on her way from home to Unimap to campus, you all have until next Monday to submit today's attendance form. Okay, so please take note of the chance that is given here. Okay, starting from next week, basically I will not entertain any more excuses. If you got matters regarding health or something, please let me know beforehand. Okay, right. Okay. So before we begin our course, just quickly to share or to look at our Google Classroom platform. Okay, so if you notice, I have posted several materials under different sections for the Google platform. So please take your time, have a look at some of the materials that I have posted. Okay, so for example, for the lecture, all videos, recording videos, as well as asynchronous session or details will be uploaded under lecture section. For example, the attendance will be uploaded under lecture section. So for today's attendance form, I have uploaded the form under week 1A. It should be week 1B, sync session introduction. So please have a look. From the instructions, I mentioned that it has to be submitted before 3 p.m. every Friday. So that's the standard that we're going to do. For sync session on Friday, you have until about 3 p.m. to submit your attendance form. For a sync session, which is on Monday night, so I usually give plenty of time because it's at night. I understand that some of you have maybe go to bed early or have other things to do. So I give until Friday morning, 8 o'clock to finish your attendance submission. Okay, so ample time, so there should be no excuses for students who have things to do, who cannot fill up the form. Okay, so please take note about this. But for this week, as I said, a special permission I will give up until next Monday. So when we have a look at this async material, we have quite a few notes that I've shared. For example, the general notes for course outcome number 1, you can have a look. This is just a summary from the textbook. And if you look at the, where is it here? For example, under tutorial, so if you already forgotten about Thermo 1, okay, if you have just taken Thermo 1 last semester, that should be okay. You are still quite fresh. But if you have taken Thermo 1 in about 2 or 3 semesters ago, you might have forgotten what you have learned. So please take some time, go to this recap problem, have a look to refresh your memory. Okay. By the way, this recap problem, you don't have to submit it, just for you to have a look and just to refresh your memory. For me, it's quite important for students to look at the tips that I've shared. Okay. The reason why, because I do not want students to repeat the mistakes done by previous students. Okay. Simple mistakes. So I'm just going to go quickly here so that you can see it. Okay. So for example here we can see that for test 1, okay, let's look at test 1. How students basically lost mark. Okay. Some of the units are not given, okay, diagrams not labeled, plots are too small, students did not read or fully understand the question, okay, especially for example isentropic methods. This is the critical part. Okay, isentropic was covered in Thermodynamics 1, okay, and yet many students basically can't remember the fundamentals of the isentropic equations or isentropic methods. Okay, and then what else? All right. Students tend to jawab cincai. Okay, for those who don't understand what cincai is, basically just you answer for the sake of answering, meaning that you don't put effort in answering the questions. Okay, even though the question specifically asks you discuss that particular problem, elaborate this problem, provide examples for this answer, for example. Okay, so it's very hard to help students when you did not give what is being asked. All right, so these are some of the notes that I've basically written down based on my teaching experience. So I really hope that you have time to have a look and basically keep in mind that we all have our own expectation. Okay, so the question is there, the tips are already there, but if you don't pay attention, so I think it's your loss. Okay. Any questions so far about Google platform or our class in general before we start again for our first class? Anyone? Any question from student? You can type your questions in the chat box or you can unmute your mic to ask question. Okay, can I just check how many of you already on campus? Can anyone know? Can someone provide response, please? Are you all in campus already, or some of you are still at home?
At home.
Yeah, home with them.
But I do hope that you guys are planning to come back on campus. Am I right?
Yes, doctor.
Yeah,
Okay, all right. So just to again to recap what was covered in the async session, the class or the lecture will be done by hybrid method, which is online class like this. We have asynchronous and synchronous session. And then for tutorial as well as for the lab, it will be a face-to-face delivery. So please make sure, hopefully, you look at the schedule that was shared, the teaching plan, so you get some idea of when the tutorial is, when the lab is, so that you will be on campus during that day. All right. Okay, so without further ado, I think let's proceed with our first lesson, basically. All right. Okay, basically the thermodynamics from Thermo 1, I think you guys are quite familiar, quite exposed to thermodynamics, the meaning of thermodynamics. So thermo is basically just heat. Dynamic is something that is moving, something that is always not static, or it can be a type of force or power. Okay, so we want to look basically how heat and this force or power work in tandem to give some applications that we use in daily life. Okay. So in short, thermodynamics, okay, based on what you have learned, It is a study between heat, work, and energy. It deals a lot with conversion of energy from one form to another. Okay, and it deals with interaction of a system and surrounding. So if you remember from Thermo 1, when we look at the closed system or maybe open system, what we are looking at basically is the principle or the fundamental of conservation of energy. So energy cannot be destroyed or created. Basically, it just changed one form to another form. So in Thermo 1, we look at how the interaction between the system and surrounding result in the loss or gain of that particular system, the energy, the overall energy inside the system. So we have positive gain and we have negative for loss. We look at the Q, heat transfer, and we look at the W for the work done. Okay, so that's from Thermo 1. So in Thermo 2, we will focus more, especially for CO1, on the principle of the heat engine. Okay, so what heat engine is, basically something that uses or utilizes heat to produce work. So this is what we are going to focus for CO1 and CO2 actually. Okay? So for CO1, when we look at the cycles for gas power cycles, vapor power cycles, and combined power cycles, we will look at some of the engine or devices that is basically involved in converting this heat into work. All right, and some of these devices, for example, is used almost daily in our life. For example, motorcycle engine or even car engine. Okay? So basically, what we have over here, heat is being supplied to the engine. Okay, the heat engine. Okay, basically, you receive the heat, and then heat engine will produce work here. Okay, but based on the principle of thermodynamics, some of the heat must be released to the environment. So basically, this is what we're going to focus, or we are going to learn the fundamental of it. Why heat engine requires some release or some of the energy to be exposed or removed to the environment. So this is what we're going to study in this course. Okay. All right. So other than that, you'll get some insight into the thermodynamics of mixtures for ideal gases, including moist air, combustion and other reactions, thermodynamics of real gases, mixtures of real gases, thermodynamic relationships, properties and data. This is quite similar to Thermo 1 actually, and chemical and phase equilibrium. So this is basically the summary of what we are going to learn, or the end of the semester. Hopefully, you can get some of these keywords or the key content that is going to be delivered for the next 14 weeks, inshallah. Okay. All right. So if you look over here, based on your understanding in thermodynamics, basically work can be converted to heat directly and completely. So meaning that when we have here, when we stir something, we have a pedal wheel over here. The movement of the pedal wheel basically will produce heat, okay, because of the frictions between molecules and also the shaft. Okay, so we have heat being produced to the environment. Okay, but the questions in Thermo 1, if you remember, your lecturer or the syllabus must ask you along the semesters the question whether it is possible for us to take the heat and do work. Basically, if we have heat from the environment and we push it into the system, can it, for example, in this case, can it move or can it spin the pedal wheel? Can heat be converted to heat directly and completely? So the question basically is here. Can we use this heat from the environment and use it to create work? So that's what we are going to look at in Thermo 2. So basically, the answers to this question, the one that we look over here, it is not possible if we just use heat and then we push it or we force it on the system to create work on its own. We can't do that. So to convert heat to work, we require this particular device that is called the heat engine. So the simplest example for heat engine is this BMW car engine, okay, or any car engine for that matter. Okay. Basically, it uses heat, okay, as we look at the example before. So let's say this is heat engine. So heat is being supplied to the system, and then work is being produced, okay, by the system, but there must always be byproduct, which is again heat. This is low temperature. So heat must be released to the environment. So this is the principles of thermodynamics that we are going to study for Thermo 2. Okay. So for the thermodynamic cycles that we're going to focus in Thermo 2, we will be looking at the power cycles. Okay, so this is under CO1, and this is under CO2, refrigeration cycle, under Dr. Nama. He's an expert in refrigeration system. So he will explain the working principles, the fundamentals of the cycle for refrigeration. For my parts, for CO1, so we will be covering basically under power cycle, we have gas power cycle, which can be further brought down into three main cycles that we are going to focus on, which is the first one is Otto cycle. Otto cycle is basically spark ignition based cycle or spark ignition based engine, where we require spark in order for the engine to work. Diesel cycle, this is again is a compression based engine. In this engine, basically, we do not require a spark for the it's not explosion, for the what you call it, the explosion to happen in the engine. So basically, for diesel engine, we require a very high compression in order for the engine to start working. Okay, so that's for compression. And Brighton, basically, we are looking at basically a combination of gas and also vapor power cycle, where we are going to look at the turbine, basically how the turbine works. Basically, for example, the engine used on an aeroplane. Okay, so that is the one that used a Brighton cycle. So it focuses on the turbine. And next, for vapor power cycle, we are going to look at one specific cycle, which is Rankine. This is basically the main cycle, but of course, some of the cycles can be improved or can be modified to increase the efficiency. So that's the main target for Rankine cycle. We're going to look at several modifications on how the efficiency of the Rankine cycle can be improved by modifying part of the cycles. So this is our target. Okay, so let's say modification A, B, and C. So that's what we are going to look at for this course. Okay. So for power cycle, basically it's just heat converted to work, and for refrigeration cycle, instead of basically we use heat for work, now heat is being transferred from low temperature region to high temperature region. Basically, we want to remove the heat from the space that we want. So that's I think it's pretty obvious. Everyone knows how refrigeration works. Basically, we want to basically, let's say we want to freeze our food. So basically, that's why the space or the freezer basically is very cold, because the cycles basically works by absorbing the heat, okay, inside the space and then remove it in the surrounding. So that's why if your refrigerator is basically quite old at your home, you'll notice that at the back usually there will be a lot of like this something, okay, at the back of your fridge, the coil basically that works as the reservoir, basically to remove the heat. Okay, that's for the old type of refrigerator. Nowadays, I think most of the coils are located at the bottom of the So this is top. So it's located at the bottom of your refrigerator. So you don't feel much of the heat basically being removed from the refrigerator. But the old one, they mostly put at the back of your refrigerator. So you can feel the heat being removed. Okay. All right. Okay. Any questions so far from students? Anyone, please?
Tak ada.
Okay.
Ada, terima kasih. Thank you. All right. Can I just double confirm? Do we have any international students in today's session? From the registration, we should have one student, which is in site. His name is Site. Site. Okay, never mind. Just 1 second. Syed Shafi Ali. Can Syed Shafi Ali confirm whether you are in this session or not? Confirmation. All right. Okay, so let's proceed. Oh, sorry, here. All right, so for gas cycle that we're going to look at or focus for this CO1, as I mentioned just now, we have Otto cycle, which is a spark ignition internal combustion engine. So usually they call it ICE engine. Okay, so for Otto, as I said, it requires spark to ignite the combustion. And this is mostly used in the petrol engine. And next, for diesel engine, it is a compression base for internal combustion engine. Compression, basically, it doesn't require spark to combust the mixture. Okay, basically, we're going to look at how piston, the ratio of the piston is very, very high that compresses or the push the mixture into combustion by itself. Okay, so that's the gist of it. Next, before we proceed, just to highlight over here the term internal combustion engine, ICE. Okay, so Otto cycle, diesel cycle, petrol, diesel, I think it's quite common. Is we understand basically the combustion happens within a closed place. Okay, but there are also some cycles that basically based on the external combustion engine, where the combustion basically happens outside of the space or the volume. Okay, so we are going to briefly cover that. Right, so just to highlight why we have ICE, internal combustion engine, because we also have external combustion engine. Okay, external. Okay. And then, of course, as I mentioned, Brayton cycle. This is basically a gas turbine engine. So basically, you can see over here. Basically, this engine utilizes the constant pressure to basically work on the principle. So if you notice on the aeroplane, okay, on the wings, basically, usually there will be two engines each, one engine each on each wing. So basically, we'll have air intake over here, okay, and then the air is now being cooled so that it increases the density. So once the air is being cooled, the density increases, then it enters the combustion chamber where the combustion happens. Then after the combustion happens, what happens is the gas or the gas expands, okay, because when we provide heat, the molecules basically spread, so the gas expand. The expansion basically will cause the turbine over here to rotate, and that's how the power is provided to the aeroplane, okay, for lift and thrust. So that's what we're going to look at for the Brayton cycle. Now, so that's for the vapor, gas, and combined power cycle. The next one, we are going to look at the vapor power cycle. So specifically for the Rankine cycle. So Rankine cycle is basically used usually in the power plants, okay, because it's huge. Okay, it requires a combination of several devices to make this work. So if you look over here, on, let's say this is A and this is B. Okay, let's look at A first, diagram. So basically, this is the simplified schematic diagram of how the power plant works, basically. Okay, in Malaysia, I don't think we see this cooling tower. I'm not sure whether, I don't think any of the power plants, the coal generation, the coal power plants in Malaysia, I don't think we have the this cooling tower. But if you watch a lot of movies, especially for a Western movie where there is a apocalypse that involve nuclear power plants or nuclear weapons, usually you will see this type of cooling tower. Okay, because this is basically used a lot or presence a lot in the Western countries. Okay, so this is a basically cooling tower. All right. So basically, how does it work? The principle is quite simple. It's quite similar to the one that we briefly discussed on the jet engine. Okay? So basically, we have a reservoir. A reservoir basically is a collection or a large body of water. Okay, basically the large body of water, like for example, ocean, river, okay, where the temperature doesn't change that much. Okay, basically it's very hard to influence the temperature in the river or water because the volume of water is so large. So it takes a lot of energy to change that properties, okay, which doesn't happen a lot. Okay, now, so this water basically being run through the pump, okay, to increase the pressure, then okay, basically goes through this component. Okay, before we go to this component, let's look at how electricity is generated. So we have the electric generator over here. So this is the electric generator, which basically goes to your pencawang lah. Pencawang basically if you have a tower, basically all the connected parts. Okay, so that's how electricity is generated. We have electric generator. So what drives the generator? So that's the important part, which relates to thermodynamics. Okay, so the generator is being basically driven by the turbine. Okay, so this is a simplified diagram. Sometimes a power plant might have more than one turbine, 2 or 3 turbines. Okay, but later on, when we look at the Rankine cycle in detail, we will study or we look at how basically adding more turbines do not guarantee or do not necessarily means more power will be provided. Sometimes there is a limit, maybe 3 or 4 turbines maximum. More than that, basically the power output does not reflect or does not basically give cost benefit to the power generation. Okay, so this turbine basically will rotate the electric generator, and then the question is what drives this turbine? So this turbine basically is driven by the water from the reservoir just now. So this water from the reservoir basically will pass through this. This is again a turbine, okay, up until here. Now this is the coil. Okay, now this coil basically when the water passes this coil, the coil is located inside a boiler. So the boiler basically the purpose of a boiler to heat up the water. So when the water heats up, basically when from the just water, now the water change phase from water into vapor. So if you enter here as H2, it's not H2, yes, if the water from the reservoir enter the boiler as a liquid, it will come out as vapor. Okay, because the purpose of the boiler is to increase the temperature of the water so that it changes the phase. So from liquid, we now change phase into vapor. So that vapor basically, because of the expansion of the gas, the vapor, it rotates the turbine, which in turn rotating the electric generator to provide electricity. Okay, so once the gas has done work on the turbine, basically it loses energy. Remember, at first it enters the turbine at a very high temperature, but after work is being done, it loses some of the energy. So it changes sometimes. Let's say it enters the turbine at 400 degrees Celsius. So when it comes out, maybe the temperature is down until 150 degrees Celsius. So now it needs to be replenished, okay, either replenished or condensed, okay, to move out, to change from vapor into liquid back, so that the cycle can continue. So basically, we are going to look at how basically from this complex diagram, it can be simplified into the ideal Rankine cycle, like in diagram B. Okay, in general, we will have pump, which pumps the water into the boiler. Q in is basically the heat is being supplied to the boiler to change the phase from liquid into vapor. Next, the vapor enters the turbine doing work, W out, and then is being removed into the condenser. Okay? The condenser, the purpose of the condenser is to remove the heat from the liquid into the environment, okay? Q out. And this is the corresponding diagram, or the corresponding TS diagram that we are going to focus on. Okay. Any questions from students? No? Okay. All right. So before we can go into details of the TS diagram of the Rankine cycle, Otto or diesel cycle, we need to go back to the basic, to the fundamentals, which is the PV diagram or the PV diagram. Okay. So I'm just going to go quickly over here with the assumptions that you guys are well aware of or still remember the fundamentals from Thermo 1. And if you don't, I have already given some recap problems for you to work on. Okay, so starting from this point on, we will proceed based on the assumptions that all the things that you have learned in Thermo 1 will basically, you still remember that, and will be used extensively. Okay, so I will not focus what we have learned in Thermo 1 back in Thermo 2. Okay, otherwise we cannot finish the syllabus. So we'll proceed with the assumptions that the fundamentals from Thermo 1 are still okay. All right. Okay. So for the TV diagram is quite straightforward. We have a compressed liquid on the left of the diagram, and we have superheated region on the right side. Okay. In between, we have the mixture region or the saturated liquid vapor region. Okay. And the lines over here, it corresponds for TV diagram, it corresponds to the constant pressure. So anything along this line reflect a constant pressure properties. Okay, constant pressure over here, over here, or over here. Okay, so if we have several lines in our diagram or in our TV diagram, so the top lines must always represent a higher pressure. So for example, over here we can see that P2 is higher than P1, so it reflects on the pressure, the value of the pressure. Okay, so I think it makes sense in general, because if you go look at the y-axis, it reflects the temperature. So as the temperature increases, so does the pressure. So similarly, vice versa, if you increase the pressure, temperature will also increases. So I think that makes sense. Okay. So how about the PV diagram? Okay. So the PV diagram is quite similar. We have again compressed liquid region on the left, and then superheated region on the right. In the middle, we have the mixture region. Mixture region. Okay. Okay, now, aside from that, the only difference is in terms of the lines that crosses the diagram. Okay, so instead of constant pressure, because we are dealing with PV diagram, now we have a constant temperature line. Okay, and similarly, as P increases, our T also increases. So a higher T line, constant temperature line, reflects a higher T value. Okay, so that's, I think, the basics from term 1. Okay, so again, I would like to emphasize over here, the knowledge that you have gained or that was covered in term 1 will be extensively used and applied in this course, especially for first law, second law, entropy. And this goes without saying, the use of the property table. Okay, because we will look or we will use the property tables extensively in order for us to find all the properties in their respective cycles. Okay, so please make sure that you understand what Thermo 2 is about. Okay, it is an extension of knowledge. It's not something new. It is an extension of knowledge from Thermo 1 into Thermo 2. Okay, so just quickly we go through. For first law of thermodynamics is about the conservation of energy. Basically, the change of internal energy, it can be summarized or it can be equal to the Q minus W. Okay, basically, if you want to find dE dt, okay, the change of energy in the system over time. Basically, when we are dealing with time, that's why you have dot over here, Q dot W dot, because change of time. So the dE dt basically is just whatever comes in equals whatever comes out. So that's the conservation of mass. Okay, conservation of energy, and the sum of the properties going in and out basically can be given as the following equations: Q net minus W net plus the summation of, we have H, which is the enthalpy, we have V is the velocity, and Z is the elevation. Okay? Whatever that comes in, mass goes out, okay, equals to what goes out. Okay, and just remember enthalpy H equals to U plus PV. Okay, and for the first law, this is a quick recap. General principle that places constraint upon the direction of heat transfer. So we understand about this. Basically, as we discussed previously, heat can be used to generate work, okay, but it cannot be used 100% to generate work. So some of the heat must be lost or be transferred, be removed to the environment. Okay, so from hot reservoir, so this is T high. We must have T low, okay, for us to generate the work. Okay, so if you just have T high and then you want to use it to have 100% efficiency so that you can generate work, okay, this is wrong, or this will not work. Okay, so it violates the second law of thermodynamics. Okay, and similarly, this is for refrigeration cycle. Basically, you cannot basically cool up or cool down the hot reservoir by transferring the cold temperature into a higher temperature to cool down the hot reservoir. You cannot do that. So you need helps from the heat engine, or in this case, work done. We need a work done on the system in order for you to achieve a refrigeration cycle. So that's about first law of thermodynamics and the second law of thermodynamics. Okay. About entropy, just a quick recap. So entropy basically a measure of amount of energy which is unavailable to the work, or in the simplest term, basically is a chaos or random movement of the molecules. Okay, I usually give an example of a simple thing. Basically, if you have a room, okay, and let's say this is your hostel room. Okay, if you just basically live in this room and you did not tidy up, so what will happen after a while? Your room will get messy. Okay, because of the random movement. Okay, you move some things, you move your pillow, you move your shirts, you move your shoes. So basically, what happens is over time, your room will not be getting tidier if you don't tidy up. So it will not get tidy by itself. So over time, by principle, you will move things. Okay, random things will happen, chaos will happen, so it will get messy. So that's the general principle of entropy. Okay, and then again from Thermo 1, it's all about the math. Okay, the equation is not just math, equation. Okay, basically, we learn about Q in, Q out, W in, W out. Okay, what is the positive sign? What I want to highlight is here, the sign convention. So this is very, very important. Okay? For example, Q in is positive, Q out is negative. W in is positive and W out is negative. So these are the sign convention that we basically use in thermo 1 that will be used again here. Okay, okay, so before we go further, just a quick introduction to some of the terminology that we're going to use a lot in thermo 2. Okay, the first one is isobaric. So isobaric refers to the term constant pressure. Okay. So when the question mentioned, okay, for example, this system is isobaric. So it reflects or it means the system is basically is a constant pressure system. So constant pressure is quite straightforward. What you'll have over here is just a straight line. So if this is P and this is V, V is volume. So for constant pressure, that means from point 1 to point 2, the pressure doesn't change. Okay? So remember, for isobaric, it reflects or it refers to a constant pressure. Okay. Next, the term isochoric. Okay, isochoric refers to the term or refers to the phenomena where the volume is constant. Okay. When we deal with P and V, so if you have this is state 1 and this is state 2, if the system is in constant volume, means that volume 1 equals to volume 2. And when that happens, what you will have is a straight line. Okay. So that's about the constant volume. So for constant volume, okay, if you notice here, there is no area under the curve. When there is no area under the curve, usually it means there is no work being done. Okay. In contrast, over here, because there is an area under the curve, okay, it reflects the work being done. Okay. All right. The next one is the term isothermal. Isothermal means we are dealing with a constant temperature system. Okay. So for constant temperature, so what you'll have is if your delta U, the change of internal energy equals to 0, what you'll have is just Q equals to negative W. Okay. So over here, if you look at the definition or the equations, because there is no area under the curve, means that W equals to 0. So your delta U equals to delta U, internal change of internal energy equals to the work, the heat transfer Q. And now, if you look at these equations, okay, because now we have area under the curve, so we have work, and work can be calculated by using these following equations. Negative P, which is the pressure, multiplied by delta V. Okay. So when you rearrange, what you're going to have is delta U, the change of internal energy, equals to Q minus P delta V. Delta V here refers to the W. Okay. So remember, it's all about the understanding of or translating what you understand from the plot. So isobaric, constant pressure, you will have a flat line. So area under the curve, so you have W. For isochoric, constant volume process, there is no area under the curve, so your W is 0. Next, for constant volume, for constant temperature, isothermal, because your delta U, the change of internal energy equals to 0, your Q equals to negative W. Okay. And next one, adiabatic. Okay. So adiabatic says, or it translates to, there is no exchange with the environment. Okay. Where can we use this? Okay. For example, in Rankine cycle just now, when we briefly have a look, there is a boiler. Okay. There is a boiler as one of the components. Okay. How can we increase the efficiency of the boiler? Okay. One way to do that is by using insulation. when we insulate our boiler, for example, this is just a rough sketch. When we insulate our boiler, we intend, or the plan is to avoid heat being transferred out. So we want Q to be 0, okay? Because we want to increase the efficiency. Otherwise, we have fuel, we'll have gas, and when the combustion happens, if the Q, or if there is a heat transfer, meaning that there is an interaction between system and environment, we will keep on losing heat. When that happens, what will happen is we need to keep on pumping fuel. Hence, it will be inefficient because we are spending too much money on fuel, yet the efficiency is low. So that's why in the cycles, what we are interested in mostly is how to increase the efficiency. That's the keyword. It's all about efficiency. Okay? So adiabatic means there is no heat transfer from the surrounding. So no heat exchange from the system. This is the system inside, and the surrounding. Surrounding is outside. Okay, so let's take a 5 minutes break, and then we will continue with our lecture. Thank you. Okay. All right. So it's now what we look at. So I pick one. So now that we understand some of the terminology that we are going to use in Thermo 2, so let's look at the introduction or the brief overview of the cycles that we're going to learn. Okay, so in general, this is basically the fundamentals or working principle of the engine. Okay, so in general, for four-stroke engine, will have four cycles, which is the intake, compression, combustion, and exhaust. So this animation basically shows you how the engine works based on these cycles. So just take a moment to understand from number 1, intake, and then after that, compress. After compression, then you will have the spark, then combustion happens, then exhaust. Okay, so this is the principle of the four-stroke engines, and in this case, this is for Otto cycle because we have spark. So that's the easiest indication. Okay, because we have spark, then that's the Otto cycle. And in general, the one that you look at over here is just a small portion of the engine component. So the purpose of learning about all this, and the purpose of we discussing this, is so that we all understand the beauty of the engineering that was done on a car, for example. Now we are talking about a car. So it involved a very, very complex mechanism, a combination of several complex mechanisms in order for a car to work and move. Okay, so the heart of the car basically is the engine. So if the engine breaks down, if it doesn't work, then the car will not be moving. Okay, so if you look over here on the left here of the diagram, so the one that we're looking at right now is what is happening within the engine. Okay, so from there, now the movement of the shaft, okay, is being transferred. So we have all this, we have a piston moving up and down, and then we have the connecting rod, the one that you're seeing in this animation. So that's the one that is going up and down, moving the crankshaft. So the movement of this piston going up and down being transferred to other parts or other component into the crankshaft, which in turn will move the flywheel, basically moving the car, basically. Okay, because the flywheel is we put it at our wheel or tire. Okay, so as you can see over here, the combustion or the principle of the engine is quite simple. Okay, so the purpose is for us to have a combustion so that the piston will go down. So that's only one. So we need this to be repeated, okay, continuously, and this repetition is called cycle. So one complete cycle involves intake, compression, combustion, and exhaust. Okay, this is specifically for four-stroke engine. For two-stroke engine, okay, instead of four phenomena or four things going on, we only have two, okay, which we are going to cover later. Okay, so just take a moment to appreciate how these cycles, basically this repeating movement up and down, combustion, exhaust, resulting in the movement of the car. Okay, so now this again is just an animation to show basically how the crankshaft is being turned, okay, and in turn moving the car. Okay, so we have the valve. Okay, the valve, they have already basically preset timing, open and up, okay, for the intake to happen, for the exhaust to go out, and those moving up and down movement in turn rotating the crankshaft. Okay, so just imagine this is the heart of the engine, cycle itself, and then the movement of the cycles now is being transferred to the crankshaft, and it involves several very complex mechanisms, not just the one that we're looking at right now, but the overall combination that makes the car works. Then this is just a quickly, we're going to show basically how refrigeration cycle works. Okay, this will be covered by Dr. Nama, of course, but just to show you, basically, a very simple mechanism, but works in our favor. For example, we start with the compressor over here. So as you can see here, okay, hopefully you can see here, the compressor basically is the work done on the system. So without compressor, we will not be able to make the system work. So when we compress our refrigerant, okay, by the way, we call it refrigerant, okay, we don't call it liquid. The things or the liquid or the fluid inside the system, we call it refrigerant. And refrigerant, okay, in this case, we do not use water for several reasons. One of it is because of the inefficiency, and secondly, because it will corrode the system. Okay, so this refrigerant basically being compressed by the compressor, hence increasing the pressure. So when you increase the pressure, it changes phase, okay, from liquid into now superheated vapor. So now it goes by the coil, as you see over here on the diagram, passing through the coil. Okay, that's basically the condenser. So why we have this coil instead of the straight line? Because we want to increase the surface area. Okay, if you remember from heat transfer, in order for you to increase the efficiency of heat transfer, you need more surface area. So by using this coil, okay, instead of, let's say, straight line or straight piping, now you have this coil system where you increase the surface area, hence you increase the heat transfer rate or heat transfer surface area. So that's the condenser. Basically, because of the environment, let's say our room temperature, because at our house, at room temperature, because the high pressure superheated vapor, the temperature is very high, so there is a temperature difference, hence it removes the heat from the system into the environment. Next, after the condenser, it goes through the expansion valve. Okay, now, for the expansion valve, from this, let's say, by looking at the diagram, from the small intake into a larger outlet, basically it loses the energy. So from superheated, it becomes maybe a liquid. So it loses energy. So maybe not liquid, but the temperature decreases. So when the temperature decreases, okay, of course, the purpose is so that the temperature entering the temperature of the refrigerant entering the fridge must be lower than the temperature within the space or within the fridge. Okay? So again, we have a coil system because we want to increase the rate of absorption, okay, from the refrigerator. So it absorbs the heat and the cycles continue. So cycles means something that is being repeated. So that's the gist of it. Okay, so to summarize, basically, it is possible to perform series of processes in which the state is changed during each process, but the gas eventually returns to its original state. Such a series of processes is called a cycle, okay, and forms the basic understanding for engines. Okay, so anything that is repeating, that's cycle. So for in Thermo 1, I believe you covered a Carnot cycle. Okay, what is Carnot cycle? And for Otto cycle, which we are going to cover, basically describes the operation of internal combustion engine. Remember, aside from internal engine, we also have external combustion engine. The Brayton cycle describes the operation of gas turbine engines. And for the Otto, diesel, and Brayton, we will mostly use PV and TS diagram. Okay? And also, of course, for the Rankine cycle. So PV, TV, and TS will be used extensively, okay, in describing or in analyzing cycles. Okay? We will continue with basically in the textbook is in chapter 9, which is gas power cycle. So the objective for this chapter, as stated over here, so you can have a look. I have already posted the objective in the Google platform as well. So please have a look. Right? Basically, we want to check or evaluate the performance. We want to look at how, by looking at the system, we can simplify our assumptions or understanding so that we can analyze the system. As you understand, in thermodynamics or engineering applications, most of the analysis can only be done by using a certain assumptions or simplification. Otherwise, the system will be too much or too complex for us to evaluate. We will look at how the operation of engines, okay, and then we will analyze both closed and open gas power cycle. We will look at problems for Otto, diesel, okay. Stirling and Allison will be covered briefly. So, but we will focus mostly on Otto and diesel for this course, and also we will look at the problem solving for Brayton cycle. Okay, so I think that's all for the introduction. So for chapter 9, this is for the Rankine cycle. So quite similar. We analyze the vapor power cycle. We will look at how to modify the basic Rankine power cycle so that we can increase the efficiency. And then we are going to look at here. This is quite important. Reheat and regenerative vapor power cycle. And also we are going to look at this method that is called cogeneration. Okay, so this is what we're going to look at for chapter 9 Rankine cycle. Okay, so starting from next slide, or sorry, not next slide, starting from next class, please have a copy of table A17, ideal properties of air, ready. So I believe you already have this from thermodynamic course. I will also upload this in Google Classroom. So I will upload once we finish this lecture today, a copy of these property tables, because we will be relying on these property tables for analysis. Okay, so please make sure you always have these property tables ready, open whenever you have thermo class. Okay. So every time when you have a class, please make sure you have the property tables ready, calculator, and a few sheets of paper so that we can do practice problem. Okay, so recap thermo 2. Again, I've posted the samples in Google Classroom, so please have a look. So the next one, we are going to look at the details applications or the details working principle for Otto, compress, and also other cycles. Okay, any questions up until this slide from students? Anyone? All right. If there is no question, so let's proceed with the chapter 9, gas power cycle, right? Okay. All right. So let's continue with our lecture. Now we are going to start looking at the first cycle that you are going to learn for this semester. Okay, so this is the chapter 9, which is the gas power cycle. Chapter 9 here refers to the textbook by Chengel that I've shown or I've shared before. So other textbook may refer to other chapters, so please be aware. So chapter 9 here refers to the Chengel textbook, Thermodynamics. Okay, so we discussed briefly on the objectives. So we want to look basically the operation of the cycles. We want to analyze the cycle, and we look at some problems solving for these cycles. Okay, so in thermodynamics, when we analyze several cycles, usually we start with the totally reversible cycle. Okay, if you remember, reversible cycle means something that can be reversed to the original position. Okay, so in contrast to reversible, we have irreversible. Okay, irreversible means once we start a process, we cannot move back to its original position. Okay, and that's what happens usually. Okay, so in thermodynamics too, when we look at the cycles, we analyze or we make an assumptions that these cycles basically is or are reversible. So meaning that it is not possible to be achieved in real life. Okay, but for the purpose of analysis, so that's one of the assumptions that we make. Okay, so when the cycles, when we discuss the cycles in thermodynamics 2, we always keep in mind that these are reversible or totally reversible idealized cycle. They are idealized because they cannot be attained or cannot be performed or cannot be basically replicated in real life situation. Okay, all right. So these theoretical cycles cannot be attained in actual. They have performance characteristics that can approach to some extent in real life, but never fully achieved. Okay. However, the ideal cycle, like the Carnot cycle, present an optimal or best case scenario. So that's why sometimes when, let's say, you become an engineer, you want to create a new engine, for example. To create a new engine, you understand that your engine cannot be 100% efficient because it's almost impossible to get that. Okay, almost all thermodynamics law mentions that to achieve 100% efficiency is almost impossible in real life. Okay, but in order for you to check the performance of your engine, you can check the theoretical condition. Okay, in theory, for example, you want to check what is the best case scenario of your engine or your design. So to do that, usually they use a cycle that is called a Carnot cycle. So Carnot cycle, this is again idealized cycle. It's impossible to achieve in real life, but it can give you some indication of the performance or the expectation of the efficiency for the design. Okay. So for this Carnot cycle, they have the maximum possible thermal efficiency and performance for the conditions and consists of reversible processes with no friction, etc. So again, I think by now we all understand friction happens everywhere, okay? In the engines, even when we are walking. So it's almost impossible to create or to design something that doesn't have a friction, even by using lubricant. Okay? So that's why these reversible processes is not possible to be achieved. Okay? As for example, they give you one example because they assume no frictions to happen. Okay? Common practice to refer to a real device as operating in one of the named ideal cycle, even though in actuality it deviates substantially from the device or from the ideal, with a lower efficiency and high entropy generations. Okay? So basically, just keep in mind the cycles that we are going to focus on from here on. Basically, is the ideal cycle. Ideal cycle means we simplify the cycle for the purpose of understanding. Okay, as you can see over here on the PV diagram, it shows the deviation or the difference between the ideal cycle, the one that we're going to use for analysis, and the actual cycle. you can see there is some obvious deviation happening. Okay. So the thermal efficiency for an ideal reversible heat engine, as mentioned before, cannot be better than the Carnot cycle. So the efficiency is defined as W net out divided by Q in. So Q in is the amount of heat being forced into the system, and W out is the work that can be generated from the Q in. And we understand that the W out cannot be even 100%. So it must be lower than Q in because there will be some losses, even for idealized cycle. So this W net out equals to Q in minus Q out and divided by Q in. And when you simplify it, you can write down 1 minus QL. QL refers to Q low, out, because out is lower than Q in, and Q in can be defined as QH, a higher heat transfer. So the actual cycle efficiency compared to the idealized cycle thermal efficiency is reduced by many factors, such as we mentioned, friction, operation under rapidly changing non-equilibrium condition. So if you have a system that moves very, very, very slowly, and at in equilibrium, then it might be possible for you to achieve idealized cycle. But just imagine if our piston is moving very, very slowly, then how are we supposed to drive at 100, 120 kilometers per hour on the highway? So other than that, why it is not possible for idealized cycle? Because of the heat losses resulting from inadequate insulation and other irreversible factors. So these are some of the issues on why on the real application is impossible to achieve idealized cycle. Okay. The first thing that we need to understand, or that we need to make, one of the assumptions are called the air standard assumptions. Okay. So certain simplifying air standard assumptions are often made to model the so-called air standard cycle. Okay. So these are the assumptions that made. Okay. And the purpose of this air standard assumption is to simplify the analysis of the gas power cycle. Okay, so the assumptions are stated as follows. Okay, the first one, so the working fluid that we are dealing with is air and not the real fuel plus air mixture, nor is it a liquid gas mixture which continuously circulate in a closed loop and always behave as an ideal gas. So the first assumptions is very, very critical, because we understand that which we will explain in a bit when we deal about compressed engine or spark ignition engine. The combustion happens because of the spark from the spark plug, which basically combusts the mixture between fuel and also air. Okay. But now, to simplify our analysis, instead of considering the mixture, we consider the working fluid, which is the mixture in the chamber, in the piston chamber, is just air and not air plus fuel. Okay. So the other important keywords from this assumption, the first one, is about the circulation. It says here, continuously circulates in a closed loop and always behave as an ideal gas. Okay. So that's why this is important, important assumption, because in real life, when you look at the animation just now, which again we are going to look later in detail, there are two valves, okay, for each piston, for the intake valve and also for the exhaust valve. So by right, in real applications, the cycle itself is not closed. It's an open loop, because we have intake in gas fuel mixture, and then we have out due to the exhaust. Okay, but for simplification, it is assumed to be closed loop, and again, because we assume we are dealing with air, it behaves as an ideal gas. If we don't make these first assumptions, what happens is that we have to consider the properties of the mixture, which is now air plus fuel. So the chemical compound of the fuel, we need to understand that. We need to take into consideration the temperature. So it will be almost impossible or nightmare for us to solve this problem. So the second assumptions, or the second assumption related to this air standard cycle is about the processes that we are dealing with are internally reversible. Again, we assume it to be idealized cycle. In real life, it is irreversible. Okay, we cannot get, once we move the piston, we cannot get back to its original position, or the properties will already change. So the third one, the combustion chamber process is replaced by a heat addition process, which adds heat to a heating section from external source. Okay, so let's say for the Otto cycle, so we understand that for Otto cycle, it is a spark ignition cycle. We have a spark plug on top of the piston. So once the piston reaches the top dead center, which we are going to look at in a bit, so once it reaches a certain position, the spark plug will basically give a spark, and the combustion happens. So that process is now being replaced by heat addition process, which is Q in. Okay, so that's simplifications. And then the next one, the exhaust process is now being replaced by heat rejection process. So as I explained just now, when there is a opening on the valve after all the processes are complete, when the mixture or the gas is being removed outside, so that exhaust process is now being replaced by Q out, heat rejection process. Okay? And finally, in addition, it is also assumed that air has constant specific heat determined at a room temperature T equals to 25 degrees Celsius. Okay, so that's basically the assumptions that we make before we can go into details looking at the TS or PV diagram of the cycles that we're going to look at. Okay, so please understand why these assumptions are necessary. So without these assumptions, it will be a very complex process for us to analyze. Okay, so if you've got any questions, please let me know. Okay, so before we go into details looking at the cycles, it's important for us to understand the terminology as well. Okay, so this is the basically the section. Okay, they cut the piston area to show you basically how the pistons looks like okay, within the chamber. Okay, so before we go into details, so let's look at some of the components so that we understand when we discuss the cycles, all the processes that relates to the cycles can be understood better. Okay, so let's look in detail on the basically from the cut off here that we look. Okay, what are the important components that makes up the piston and also combustion area? Okay. So the first one, you can see that we have valve on top here. Okay, just give me 1 second so that I can share my pointers. There's a pointers. Okay, I hope you can see my pointers. All right. So you can see that this is the intake. So the intake here refers to the intake of air-fuel mixture. Okay, air and fuel is being mixed. Okay, it goes inside. So now this is the cylinder. Okay, the component over here, and the piston is here, similar to what we have over here. These are the rings. So if you look at, okay, if you go back to this slide, if you look at this pistons over here, you notice that the piston is not just a smooth block. Okay, it has some groove. Okay, groove means there's an opening lah. Okay, so basically it's not just a flat surface. There's a groove on the piston, several groove actually. So in this case we have 1, 2, 3, or maybe 4 groove. Okay, the purpose of the groove will be explained in a bit. So this piston is basically the groove. Okay, the groove basically for us to put the rings on it. Okay, and the purpose of the ring basically so that if you notice over there, the piston is basically tightly fit. Okay, of course it must fit within the chamber or within the cylinder, but not not by touching the cylinder surface. So otherwise the friction will be too big, too high. So to prevent the mixture of the fuel from the top here going down, this is oil, okay, down here. So they put rings on the groove. So the purpose of the ring is basically to prevent the liquid or the oil down here from mixing up with the air fuel mixture at the top. Okay. Then we have a wrist pin, basically that part of the connecting rod. So we have a connecting rod touching with the crank pin with the crank. So wrist pin basically connects the piston with the connecting rod, okay, as well as the crank line, basically part of the arrangement. Okay, so this movement up and down basically rotates the crankshaft down here. Okay, and then of course we have the crank face at the bottom. Now when we look at the right side, this is quite important because this will be used in the analysis. Okay, these two, the one that you look over here, these are the valves. Okay, intake valve and also the output valve, exhaust valve. So bore refers to the diameter of the piston. So in engine terminology, they don't call it, what is the piston diameter? It's very, very rare. They call it bore. Okay, so bore refers to the diameter D. Then, of course, when you have an intake, so when you have an intake, the position of the piston is at the bottom. Then when it goes up, if the piston is closed, you have a compression. Then there should be spark plug over here. Spark happens, combustion, so it pushes down the piston. Then after that, it goes up to complete the process with the exhaust delivery. So exhaust will go up this way. Okay. So now the other parts that is important is what we call as the clearance volume. Okay. So the clearance volume basically is the position between the valve here, the top here, and the face of the piston. So basically, the piston, when it reaches the highest position it can go, I hope you can see what I'm doing. When it reaches the highest position it can go, it doesn't go all the way up. Okay? It doesn't touch the valve, okay, because it will break the valve. So when it reaches the highest position, there is some gap between the surface of the piston as well as the highest position. So that is called as clearing volumes. All right. So the highest position that the valve can go up until here, that's what called as the TDC, top dead center. Okay. So the highest position that the valve can, sorry, it's not the valve, the piston can go. So the highest position that the piston can go is called top dead center. The lowest position that the piston can go is called bottom dead center. So up and down. So the highest, top dead center, bottom dead center is the lowest. And the distance covered between top dead center and bottom dead center is called as stroke. That's why when you call it a full stroke engine, what happens is it means you have 4 movement up and down, 4 stroke. So you have intake, compression, combustion, and exhaust. So 1, 2, 3, 4. So that refers to 4-stroke engine. Its stroke is the movement or the distance covered from top dead center to the bottom dead center. Okay, so that's, I think, generally covers the important terminology that we should understand before we go into the cycles. Okay. Again, I think piston ring, I've explained a bit. So the function is as follows: to seal the combustion chamber so that there's minimal loss of gases, to improve heat transfer from the piston to the cylinder wall, and maintaining proper quantity of the oil between piston and the cylinder wall. Okay, and of course regulating engine oil consumption by scraping oil from the cylinder wall back to the sump. Okay, so that's the purpose of the ring basically. Okay, so as you can see over here, you can see here, these are the locations of the ring. Okay, basically it's located on the groove that we see just now. So basically the function as we discussed just now, to seal, to improve heat transfer, because remember the piston itself doesn't touch the cylinder wall 100%. Okay, So it acts as the conductor to transfer the heat, to basically remove the heat from the piston to the cylinder wall. Okay, because otherwise the heat inside the chamber will be very, very high. Okay, temperature will be very, very high. Okay, and of course, other than that, to maintain, to separate the two space lah, gas space at the top and oil at the bottom. Okay. Have you got any question? Just shoot, please ask. So, okay, again, I'm not going to go into detail. We discussed about the function, gas sealing, lubrication, heat transfer, as well as to support the piston. Okay, so that is the position of the piston doesn't change in the chamber. Okay. All right, so let's go into the first cycle, which is the Otto cycle. So this is Otto cycle is the idealized cycle for spark ignition internal combustion engine, which is reciprocating engines, and we use this a lot in automobiles, lawnmowers, etc. The typical larger SI spark ignition engine found in Ottos has a 4-process cycle named by Nicholas A. Otto. This is the inventor. The term Otto cycle appears to be applied to the ideal cycle. Remember, when we talk about the cycles in thermodynamics too, Otto, diesel, etc., it refers to the ideal cycle, meaning that it's impossible to be achieved in real life, but for the purpose of understanding the cycles, we simplify to make it easy for us to analyze the cycle. Okay? They are all ideal cycle. Okay? All right. So Otto cycle is actually approximation of the idealized cycle. Okay, Otto cycle engines, like many of the other power cycle engine types in the summary, highly diverse and mature technology. So as you understand, we have been using this Otto cycle for hundreds of years. So it is considered as mature technology. So what is not a mature technology, for example? Is electric vehicle. Even though Tesla, for example, almost all major car manufacturers like BMW, they are all moving into the electric vehicles market, but the technology itself is still not mature. In technology maturity refers to where almost all the vehicles basically are using the same technology. Okay, so even though yes, we have come very, very far in terms of the applications of electric vehicles, but the technology itself is not mature. There are still a lot of improvements that can be done. So that's an example of something that is not yet mature in terms of technology. Okay. So the 4-stroke engine, also known as a 4-cycle engine, is an IC engine in which the piston completes 4 separate strokes. Okay, so the strokes are as follows. So the intake stroke here refers from the top dead center, it goes to the bottom dead center. So in this stroke, basically, the intake valve must open because to allow the air-fuel mixture. So in Otto cycle, what happened is during the intake stroke, the air plus fuel mixture. So please do not be confused. Not just the fuel. It is a mixture between fuel plus air into the chamber. So that's intake. So it goes down. The valve is open. So the mixture of air fuel is being pushed into the cylinder. Okay. Next, after that, we have a compression stroke. So the compression stroke is started from the bottom, which is the bottom dead center. So once it ready, it goes up, okay, for the compression to happen. And remember, the compression doesn't go all the way up until the valve. Okay, it stops at a certain distance that is called as top dead center. Okay, it doesn't touch the valve straight away. All right. So for the compression stroke, it compresses the air fuel mixture in preparation for ignition during the next stroke, which is the combustion. So when you compress, you need to remember you need the pressure to increase. So the valve must be closed, okay, during the compression. Okay, so intake, valve open, mixture comes in. Next, it close, compression happens. All right. So for the combustion, expansion and power stroke. So basically it's the combination, because once you compress and then just before it reaches the top dead center, then the spark basically happens, igniting the mixture. Okay, so once it ignites, what will happen is basically the pressure will push down the piston. Okay, so expansion or the power stroke. Okay, because it gives the power, it push the piston down. Okay, so once it push the piston down, it reaches back to the bottom dead center. Then finally, to complete the cycle, it push up because of it want to remove all the mixture. So that's the exhaust stroke. Okay, the piston again returns to the bottom dead center and then to go to the top dead center while the exhaust valve is open. Okay, so this action expels the spent air-fuel mixture through the exhaust valve. And now the cycles will continue again and again. Okay, so this is what we looked before. So just take a moment. So let's start from 1. Intake, valve open, and then compression, spark, and then it pushes down, and then it removes the exhaust. Okay, all right. Okay, so in comparison to the 4-stroke engine, 2-stroke engine only has 2 strokes. So instead of 4 processes. So it can, if you can see over here, so top dead center to bottom dead center is exhaust and intake, and BDC to TDC is a compression and ignition. So 2 processes at one time. Okay, so you can see over here, inlet port, exhaust port. Okay, usually for 2-stroke engine, they use it on something or applications that is small, like lawnmower, for example. Okay, so 4-stroke engine is mostly for larger applications like car. Okay, 2-stroke engine, you can see here, it's very, very simple. Okay, and the size itself, the engine is very, very small. So in terms of power output, of course, you cannot compare 2-stroke with the 4-stroke engine. Okay, because of the size itself is different. Okay, all right. So example of 2-stroke engine, chainsaw, snowmobile, some applications that are very, very small. Okay. As for the old technology, this again relate to cycles that we are going to learn. So previously, in old applications of automotive, they use carburetor. Carburetor is basically where the fuel mixtures with air. Okay, but instead of having something to regulate the fuel or air coming inside the chamber, it depends on the throttle. So if you push the throttle more, then more opening is being available, hence more air is coming in and fuel is being released over here. Okay. So this technology basically is not fuel efficient because there is no specific guideline, or it's not specific guideline. There's no specific something to regulate or something to control the amount of fuel and air mixture into the chamber. Okay. But some of there are some applications that still uses this old technology, carburetor. So for example, is the NASCAR, for example. Okay. In a NASCAR or race application, they don't really care about the fuel mixture. Okay. All they care is about more power. So more power that can be generated, more faster that they can go. So that's why one of the applications that still uses carburetor in the vehicles is NASCAR competition. Okay. All right. So in contrast to carburetor, right now in the modern technology, most of the car have this already. So they use this fuel injector. Okay. So if you notice over here, near the piston, here this is the cylinder. Okay, this is the chamber. So this is a very, very complex. So you can see here why some applications still uses the carburetor, because carburetor is simple. It's all depending on the opening and also the pressure. So the more air, more fuel, you get more speed or more power. So in contrast to the modern technology, fuel injector system, you have these all components here in order for you to provide the amount of fuel necessary. So for example, if you push your throttle more, then the system basically will pump more fuel inside here. So if you can see here, just before the valve over here, okay, this is before the this is for the intake valve. When the valve open, so the location of the fuel injectors is basically just outside of the valve. So it pushes the fuel inside the chamber along with the air here, okay, into the chamber. Right. So let's look briefly at the cycles that we're going to learn. Let's take a moment to look at this Otto cycle or spark ignition cycle, where it compares the blue and the yellow one. The yellow one using the air standard assumptions, basically an idealized cycle. The green one basically is based on the real cycle. So the real cycle, this is how it looks like on a PV diagram. And the one that we're going to use for our analysis is here, based on the air standard assumptions. Okay? So from all the strokes that we discussed, all the processes, intake, compression, and then power or expansion, and then exhaust, all that, if you remember the air standard assumptions just now, it all can be simplified into the following. Isentropic compression from 1 to 2, and then Q in here refers to the combustion ignition. So Q in, and then we have V equals to constant heat addition, and then we have the piston coming down, isentropic expansion. Then we have Q out, which is the exhaust, which is constant heat rejection. Okay, V constant. Okay, in this case, V are constant. Okay, so on the PV diagram, this is how it looks like. 1 to 2 is isentropic compression, and then 2 to 3 is heat addition process, constant volume. And then we have isentropic expansion, and then finally exhaust Q out. 4 to 1 is constant volume process of exhaust. So this is what we are going to cover in this course. Okay, compared to this, just imagine the complexity that we want or we have to do in order for us to fully replicate or fully analyze the real working condition. Okay, so take a moment to appreciate how we simplify for compression stroke to be isentropic compression, how we simplify this expansion stroke into this heat addition process, and exhaust into this isentropic expansion, and finally intake stroke into this heat rejection process. So these are the corresponding idealized cycle. Okay. Okay. So I think I'm going to stop here, and let's see if we got any questions before we proceed for the next class. Anyone has any questions about what we just covered? See. Any question for anyone? All right. So if there are no questions from students, so I'm going to stop for today's lesson. Let's stop until this slide. Okay, for next week on the asynchronous session, I will post a video of my previous lecture so that you can continue from here on to cover about the Otto cycle. Okay, so that when we meet again next Friday, we will continue basically where we left off. So I'll try to provide information on the contents that you should cover for a synchronous session. Okay, so that when we start meet again next Friday, we can proceed from where the video stops. Okay, so I think that's all from me for today. Thank you everyone for joining this session. I hope we'll have a good semester ahead of us. All right, thank you everyone. Assalamualaikum and very good day.
Waalaikumsalam. Thank you, Otto.
Waalaikumsalam. Thank you, Doctor.
Thank you, Doctor.
Thank you.